today I'm going to be presenting Physics 2 Lab 4 on Faraday's Law. So the purpose of this lab was to explore magnetic induction and eddy current. So I did this by observing how a bar magnet falls through an aluminum foil tube and comparing my real world data with a computational model I built using GlowScript. So in my system, the magnet and the aluminum tube are the focus, and everything else like the air and external environment is considered part of the surroundings. So in the experiment, the fall time of the magnet was 1.254 seconds, whereas in the simulation, the magnet fell in 0.861 seconds, which gave me a starting point for analyzing potential discrepancies. So this slide lays out the core physics concepts that guided my thinking. So like first is Faraday's law, which says that the changing magnetic flux through a loop induces an EMF. So the equation includes a negative sign, and that's Lenz's law. So that shows the induced current resisting the change that caused it. And so since faster flux changes mean stronger F. And so there's also the Biot-Savart law, which tells us how current in a conductor generates a magnetic field. So it's used for complex shapes, especially when Ampere's law doesn't apply. And I also reference Newton's laws, especially the second and third. So the net force changes in momentum over time, and for every action there's an equal and opposite reaction, which is really important when thinking about how the bar and magnet in the tube react. And so this is my procedure. So for my procedure, I simply dropped the magnet through the tube and recorded how long it took for it to exit. And what's interesting is that the magnetic force that slows the magnet down isn't there by default. It's created by the induced current in the tube. And so in terms of my assumptions, I treated air resistance as negligible, and I assumed that only forces acting were gravity and the magnetic response from the eddy currents. Also, I modeled the bar magnet as a dipole, which simplified things for both calculation and simulations. And so this slide summarizes the physical measurements and the data that I worked with. So the aluminum tube width and thickness, the inner and outer radii, and the magnet itself had like a mass of 0.023 kilograms, and its magnetic dipole moment taken from lab 3, which was 4.375 ampere meter squares. And so the average fall time across trials was around like 1.25 seconds, which I used as the Curie experimental reference when comparing it to my GlowScript model. So here is the GlowScript model. In GlowScript, I built a model that allowed me to calculate both the magnetic and the bar magnet, magnetic field of the bar magnet, and the magnetic force of the tube that exerted on it due to the induced currents. And so this helped me simulate the magnet's motion and visualize how it would behave if everything behaved ideally. So that means like if no air resistance or measurement delays. The simulation clearly showed that the slowing effect of the eddy currents and how the induced magnetic field opposes the motion of the magnet. And the fall time in the model was way shorter in reality, which led me to investigate why, which I will go over later. But here I just want to emphasize how the gravitational force is greater than the magnitude of the magnetic force. And here they're equal, and here they're not again. So the simulation questions and some interpretations that I had. So I used a simulation to explore scientific questions. So first, based on Lenz's law, the red current represents the counterclockwise flow, while the blue current represented the clockwise flow. So when I flipped the magnet, the directions of the induced currents also reversed, which perfectly followed Lenz's law again. And the simulation fall time was slightly faster than my measured time, and that made sense because the simulation didn't factor in things like air resistance or drag. Air resistance or friction. And the graph in the simulation also revealed that the gravity dominates at the beginning. At the end of the magnet's fall, it's balanced by the magnetic force while the magnet is inside the tube. And you can see that over here. And some errors and further discussion. So there were a few potential sources of error. Sometimes the magnet would hit the sides of the tube, which definitely slowed it down. And I also had to manually start and stop the watch, so some timing inaccuracy was definitely expected. And so further analysis, I thought about what would happen if the tube had almost like no electrical resistance. So in that case, the induced currents would be stronger, which would create a stronger magnetic field to resist the magnet, so it would fall even slower. And on the other hand, if I cut vertical slots into the tube, the path of the ring currents would be interrupted, and that would reduce the magnetic drag and let the magnet fall faster. So thinking through these what-if cases definitely helped me understand how sensitive the system is to the tube's physical properties. Thank you.